Okay, this question is about the electrophilic addition of alkenes with H2SO4. We're looking at question 3, 2022, paper 2. This question is about 2-methyl-but-1-ene. Name the mechanism for the reaction of 2-methyl-but-1-ene with concentrated sulfuric acid. Outline the mechanism for this reaction to form the major product. And give the name of the mechanism, and this is worth 5 marks. Now, there is another step to this mechanism which they don't require here, which is if you add cold water, you actually end up with an alcohol, but that is not included in the stem here. So we just need to do the first part of this mechanism, and we need to write out the structure of 2-methyl-but-1-ene first. I know I've got a bit of a dodgy methyl group attached there, but I just couldn't really draw it with the writing properly. Okay, so we've got concentrated sulfuric acid, so I need to draw the structure of sulfuric acid next. Sulfuric acid here, obviously, H2SO4, so I just want to make sure I get the structure right. And it's a structure that you need to learn off by heart because it's got those 2 double bonds. It's a slightly unusual structure. And just check you've done 1 sulfur atom, 4 oxygens, and 2 hydrogens. And it's remembering the structure of sulfuric acid that actually makes this mechanism one of the hardest ones for alkenes. Okay, so we've got a slightly positive charge on the hydrogen atom and a slightly negative charge on the oxygen atom on the sulfuric acid. And of course, that means that this electron-rich region of the double bond is attracted to that slightly positive hydrogen. So 2 electrons move over to form a bond with the hydrogen. Now, as hydrogen can only form 1 bond, it has to break this bond that it has with the oxygen on the sulfuric acid. Now, there are 2 possibilities here of the carbocation, the intermediate that can form. Now, you don't need to write these in the mechanism, but I'm going to go through with them just so you can see what the 2 possibilities are. And it does come in later in the question. It will help us out anyway. So I'm going to do that on the side here. And I'm going to call these 2 carbocations, which are the intermediates, A and B. So in the first one, I'm drawing carbocation A. I've had the hydrogen join the first carbon with the double bond. So we can see the hydrogen is attached here, which I've circled in blue, and it's attached to that carbon. Okay, now this, that's the hydrogen there, circled in green, that has attached. And the other carbon now only has 3 bonds and has a positive charge, and this is the carbocation, this whole intermediate. Now we have a second carbocation that can form. And this is if the hydrogen instead joins to the carbon atom, the other carbon atom, leaving the carbocation leaving the positive charge on the first carbon. So we're going to draw out this formula as well for the alternative carbocation. Notice I put CH3 there. I can't fit in drawing out all the bonds. And so let's put the hydrogen here. And we're going to put a positive charge on this first carbon. And actually, there's a rule called Markovnikov's rule that can help you realize where the hydrogen atom goes. But I might do a video about that at a later date, as it's a rule that nobody uses anymore, really. Okay. So, which of these is more likely to actually form? Well, going to put a little note up there. Haven't been able to fit that in. So, this first product, I'm going to circle these 3 groups here. These are called alkyl groups. So A is the major product because it forms more of these alkyl groups, and these are electron releasing, and they stabilize the positive charge. And so that intermediate is more likely to form because it is more electrically stable or energetically stable. The minor product, product B, the carbocation there, is less likely to form. Now, why is this important? It means that it affects our final molecule. So now we're going to get on and finish the mechanism using the carbocation A. We're not going to use carbocation B, so I'm going to draw out carbocation A again down here. Okay, God, it's a pain in the backside. Right, let's draw this out. Just copy the one above. Okay, I'll do the C's and the H's properly this time. Oh, I can't fit this in. Okay, there we go. So that is the more likely carbocation. Again, it has three alkyl groups or more electron donating groups that stabilize it. Now I'm going to draw the hydrogen sulfate ion. That's what you call a sulfuric acid that has lost a hydrogen, a sulfuric acid molecule that's lost a hydrogen atom. So it has a lone pair and a minus sign on the oxygen because going back to the original draw, the first step of the mechanism, it received two electrons with that orange arrow from the OH bond. So now it has a lone pair of electrons. And this hydrogen sulfate ion is going to be attracted now to the positive charge on the carbocation, and those two electrons are going to form a bond with the carbon. And that's the end of the mechanism. So the mechanism itself will score you 4 marks, one for each of the orange arrows and the positive and negative sign on the sulfuric acid over there. And then we're going to get one for the carbocation correctly drawn and one for the orange arrow going from the lone pair and the minus sign to the carbocation. So 4 marks for the mechanism. Now we need to name this mechanism. And if you have if you have two reactants and one product, and we've got two reactants here at the start, and we're going to end up with one product once our hydrogen sulfate ion joins to our carbocation, it's going to be addition, and it's electrophilic addition. The reason being because the positive charge on the sulfuric acid is attracted to the electron dense region. It seeks out that electron dense region. So it's an electrophile. And so this is electrophilic addition. And that is the typical mechanism that all alkenes undergo, is electrophilic addition. And you only need this bit that I've circled in green. That's what you needed for your answer. You didn't really need to draw out all the carbocations. All right, let's move on. Again, like always, you might want to pause the video and have a go. So draw the structure of the minor product formed in the reaction in question 3.1. Explain why this is the minor product. So to draw the minor product, I need to draw my carbocation B, which you can rewind back a little bit if you want to have a look at it. And this is the carbocation, the minor carbocation that's least likely to form. So this was the one where it didn't have many alkyl groups. And so I put the positive charge on the first carbon. Now that's going to be attacked by that hydrogen sulfate ion. So all I need to do is join the hydrogen sulfite ion here. So I'm going to get rid of the positive charge, and then I'm going to attach the sulfuric acid minus the hydrogen because it's a hydrogen sulfate ion. And I'm going to draw the attachment here. And this is the minor product. Now, if you want to name this minor product, this is an alkyl hydrogen sulfate. And it's going to be 2-methyl, because we've got that methyl group on the second carbon, butane, because there's 4 carbons in the straight chain there, 2-iyl. 2-methyl, butane, 2-iyl, hydrogen sulfate. Forgot to name the hydrogen sulfate. Geez, that's a serious name. You don't have to name that. Let's just forget about that, yeah? Right, the major product has more alcohol groups which are electron donating, so forms a more stable carbocation. So our explanation is the reason why this doesn't form is because the major product is more stable. It has more electron donating groups, so it forms the more stable carbocation, and that will get you the 2 marks. You could write it in the reverse way and say the minor product has less alkyl groups, so less electrons released to stabilize it, so less likely to form. Anyway, that will score you 3 marks, 1 for the drawing, 2 for the explanation. Let's move on. So we're on to 3.3, draw the skeletal formula of a functional group isomer, of 2-methyl-butanene. So what is 2-methyl-butanene? Which homologous series or homologous series does it belong to? Well, you see the ENE, so it's an alkene. Can you remember the general formula for alkenes? CnH2n. And that means that we can work out its molecular formula. It's got 5 carbons, so it's going to be C5H10. And that means I just need to think of an alkane with the formula C5H10, because that will be a different functional group. It won't have the C double bond, the carbon-carbon double bond. And these cycloalkanes are the perfect functional group isomers of any alkene. So we just, cyclopentane is what we're going to write here. Now, if I had propene, I would have cyclopropane. Okay. So it doesn't contain the double bond. That's why we say it is a functional group isomer. Let's move on to 3.4 because that was just a one marker. So 3.4, 2-methyl-butyl-1-ene can form a polymer. State the type of polymerization. Draw the repeating unit for the polymer formed. Type of polymerization. Now you did this in GCSE, so we've identified already that we're dealing with an alkene, which contains a functional group that's a carbon-carbon double bond. And you should know from GCSE, alkenes undergo addition polymerization. Oh, I don't know. Have I spelled undergo? Is there an E on the end of undergo? No, I think it's right. Oh my gosh, I can't spell addition. Never mind. All right. Anyway, yeah, alkenes undergo addition polymerization. So the type of polymerization is addition. The other type that you can put as an answer is condensation, but you get a water molecule removed there. Okay, so now let's draw the repeat unit. So in order to draw the repeat unit, I want to do the monomer. I want to write out 2-methyl-butyl-1-ene again, but in kind of monomer form. So we got the double bond here, and then I'm going to draw it all out like this. Okay, so how will I make this into a polymer? There's a very simple formula to follow. Just copy the double bond over to your repeat unit. So we're going to copy the double bond over. You do this in pencil. Then add the groups onto the carbons. Leave an open ends. Those two lines are open and put the brackets through them straight away. Now I just need to take the hydrogens and add them on here from the first carbon. You're literally just transferring over all the groups. The tricky bit comes on the second carbon. Also, I've got 5 carbons around there. You can't have 5 carbons, 5 bonds around a carbon atom. So remove one of those bonds, keep that as a single bond now. And now what we're going to do is add the groups over. So I've got a methyl group here, and the tricky bit now is taking this C2H5 that I'm circling in pink. This is an ethyl group, and bending this down below the carbon. Okay, so your repeat unit can only ever have 2 carbons in the brackets. Everything else needs to be above and below. Oh my gosh, you shouldn't write CH2, CH3 like that. Okay, I'm going to put C2H5, but you could write CH2, CH3, which is our ethyl group. Just don't write it how I did, which was a bit weird. And that's the end of that. That will get you all the marks. I hope that was helpful. So as usual, like, subscribe, and let's get to the marks.
You're still here? It's over.